Alright, so we have a seemingly simple problem, right? Giving an origin and a unit 1, find the value 2. It might seem trivial to measure the distance from 0 to 1 and add this to itself so that we reach 2, but recall the nature of the measurables, the existence of the infinitesimals, and the fact that gaps necessarily lie between them. Even neglecting this, say we're just working with the reals in the Dedekind completeness sense, even taking just the nature of the measurables or their abstraction, the reals, into account, it becomes obvious that this feat is actually impossible to execute even in the idealized world of pure mathematics. Say we have an ideal divider caliper, and we set both points to 0 and 1. So 0 and 1 are defined before we set the caliper down. Okay. Pick up the leg whose point is on 0 and spin it around, holding the steady point on 1, and set the free leg back down. Is it now on 2? If not, how could you tell the difference? We define 2 as the spot that it lands on, so by definition the caliper points must now be on 1 and 2. But how can we know that the steady leg didn't slip at all during the process? Given that there are infinitely many values infinitely close to 1, simply by virtue of the Archimedean property, let alone the other previous concerns, right? So even just working with the reals, it's impossible to zoom into the points of the caliper and know for sure whether they started exactly on 0 and 1. So it's impossible to know if we measured a distance from 1, and it's impossible to know that we measured a distance of 1 simultaneously and for exactly the same reason. Thus it's impossible to find 2 with perfect accuracy by definition. If we can't even add 1 to 1, how can we find any other magnitude? Conventional mathematics employs axiomatic claims that all magnitudes can be identified with arbitrary precision, but this is always a circular claim because the result was assumed a priori. Conventionally, the naturals are taken to be the most fundamental class of magnitudes, but in truth, they are the most highly derived. If we set the caliper to some random magnitude k, and simply define 0 to be the location of one point of the caliper, then we definitely have marked off the distance k. But relating this distance to 1 with absolutely perfect precision turns out to be impossible not only in the real world, but also in idealized pure mathematics, since the relationship between 1 and k is virtually guaranteed to be non-computable. And even if the relationship between them is computable, there is no way to discern this for sure because of the Archimedean property. Even the notion of limits cannot identify the relationship between k and the unit 1, let alone any other measurement or mathematical manipulation. This follows from the fact that fewer magnitudes are computable than non-computable, a fact curiously accepted by conventional mathematics, which utterly contradicts everything that conventional mathematics is based upon. It undermines Dedekind completeness, the Peano axioms, the idea that 1 and 1 is 2, and most obviously of all, the notion that all magnitudes can be derived from defining just the unit 1.